Hello, everyone. Welcome to our 24th Zoom meeting. And I forget how many of those are roundtable workshops, but things are still going. Our subject today is reaction monitoring by NMR, and our panel will be led by Jason Hein from University of British Columbia. Before we get started, let me turn things over to John for a welcome, our sponsor, John, for a welcome.
Thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. Thank you for joining us for, as Dave mentioned, meeting number 24, Zoom meeting number 24, and just a little bit more than a year and a half into our little Zoom experiment, I guess we'll call it. And well, it's gained considerable popularity. Nearly 100 participants with us today, and that seems to be the norm for most of our meetings. Great topic material. MR Resources and Q1 Instruments are very, very happy to sponsor these meetings. We will continue to do so for forever and ever, as far as I'm concerned. And we really hope that these meetings are adding some good value to the NMR community. Our guess is that they are. Again, MR Resources, we've been around for 36 years now, providing repairs, magnet quench recovery, system relocations, reconditioned NMR systems, and so on. Q1 Instruments, a little bit more of a newcomer to the industry, but very, very capable line of NMR systems. I see Don has just joined us. Don, do you want to give a few words on Q1 Instruments today?
Great, John. Thank you very much. So Q1 is dedicated to developing NMR available across the sciences. And what we do is we sell complete systems at 400 megahertz with magnets manufactured by Q1 on license from Oxford. Complete systems up to 600 megahertz with refurbished magnets by MR Resources, and console upgrades. And this is an important introduction, a new introduction of a new economy package, which can utilize existing probes and shims for Brooker and variant systems. And what we do is we provide the console and the preamplifier, and we integrate with the Brooker or variant shims and probe. We also offer the full upgrade, which is the economy package, the console and the preamp, plus our smart tune and match probe and sample changer. So our smart tune and match probes are available for Brooker and variant systems and use a integrated Q-Link interface, which is fully integrated under Topspin and VNMRJ. I'd like to introduce some new customers. We have a silicone chemical company in Toronto, Canada, with a 400 megahertz system with a Quantum One console, a Quantum One Plus in Columbus, Ohio, with a manufacturer of dies for a major eyeglass eyewear manufacturer, and a fully upgraded Brooker 300 using the Q1 probe and shims with the dramatically enhanced 24-channel shim set, which improves the performance of spectrospin magnets. More information on all of these systems and what we can do, or want a remote demonstration, please contact us. Thank you.
Thank you, Don. Very good information to have. Everyone, please do check out this very capable line of instruments. You'll be happy that you did. Anyways, over to Krish. Krish, could you give us an update on upcoming meetings, please?
Thank you, John. Just wanted to remind everyone, next month, which is December, we are taking a break for holidays, and so the next workshop is in January. It will be led by Paul Boyer of JOL UK. The topic is benchtop NMR spectroscopy, opportunities and challenges. He'll be joined by 4 panelists: Maria Silva Elipe from Amgen, Travis Gregor from 3M, David Foley from Merck, and Kate Kemsley from Quadram Institute Biosciences in UK. Beyond that, we have a series of topics coming up until May-June timeframe. And of course, the ENC user conference will also be in between in April. With that, I will pass it back to John, and thank you.
Thank you, Krish. Continuing meetings. Well, we're going to go on forever and ever as far as I'm concerned with this. And well, I'm very excited about finally having the chance to go with a live meeting once again, day before ENC toward the end of April next year. Over to Dan, do you have some words on new software update for us?
Thank you, John. I just wanted to let people know that with the help of about 20 beta testers, we released OpenVNMR J 3.1 last month, and it a lot of bug fixes and new features. One of the new with the turmoil in the CentOS world, one of the things we focused on was to support different OSs. So this one supports like Ubuntu and Alma Unix and other things. I'll post a link to the website where you can download it, and it describes the new features there. Back to you, John.
Great work, Dan. It is very much appreciated keeping the, well, I guess we'll call it the now legacy variant equipment running, and hats off to you. Dave, if you would like to get things off and running for us, please.
Okay, before we start, I'll say that the format for our meeting is as usual. We'll have 4 speakers led by Professor Jason Hein, and up to about the top of the hour, and then we'll open things up to general questions and discussions. And you're encouraged to, at that point, to put your video and audio back on and engage in discussion. So with that picture, let me turn things over to Jason and get started.
So thank you very much, guys, and really big thanks out to the sponsors for having us today. I really enjoy the active community you guys have here and building up within Ivan. So my pleasure today to help host this event, and I'm happy to bring together 4 real luminaries in this area of this applied sort of version of NMR. Reaction monitoring by NMR is a critical aspect of looking into systems. What the amazing value here is comes from the application of this sort of space. So for today, we have a variety of people that have both been sort of developing techniques, but also applying them and using them in very creative ways. So without any further ado, I'd like to jump right into our speakers today. We're going to start with Professor Clark Landis. Now, Clark is the Helfer Professor of Chemistry at the University of Wisconsin-Madison, also the Chair of Chemistry. He received his BSc from the University of Illinois at Urbana-Champaign, and then his PhD under Jack Halpern in the University of Chicago. Since then, he has been blazing the trail both in terms of physical organic mechanistic work, but in particular his applications and really creative applications of NMR and looking deeply into reactions has been just phenomenal. Something that I've always really looked up to. So with that, again, I don't want to take up any more of his time. Clark, thank you very much for joining us today.
Great, thank you, Jason. I'll get my show started here. And my understanding is that I'm supposed to give about 15 minutes worth of talk to whet your appetite, but be prepared with lots of other slides with which to engage you. So I'd like to start off by acknowledging what brings all of us here today, and that is that NMR doesn't lie. And this is a needle point from my office. And I said this so often to my graduate students every week at our research group meeting that it's become a lore in the group. So one of our interests is in developing new enantioselective organotransition metal catalyzed transformations. And one of these is the enantioselective hydroformylation reaction that is shown here. The hydroformylation reaction is a reaction that is an old reaction. It's been around for 75 years. It is used on a very high scale. About 20 billion pounds of aldehyde are made every year using hydroformylation. And what we were interested in was applying hydroformylation through the development of new ligands to enantioselective pharmaceutical syntheses. And so here are some examples of some of the kinds of substrates that we can transform using hydroformylation. But hydroformylation is a complicated mechanism, and and we would like to be able to probe what's happening not only to the organic substrate, but also the catalyst. And so shown here is a slide, phosphorus NMR, and this is a reaction of this rhodium hydride catalyst that's shown up here on the left with styrene. And you can monitor what is happening by phosphorus NMR to this catalyst with time. The problem is these are not real in situ conditions. These are low temperatures, and the hydroformylation reaction involves two reactants, hydrogen and carbon monoxide, and this slide has no hydrogen in it. It's just carbon monoxide. So this isn't even a catalytic reaction. And this has been a problem for us for a long time. And a limitation of doing real reaction monitoring has been that if you want to look at reactions under a variety of conditions, say high pressures and high temperatures with good gas-liquid mixing, there just wasn't a way to do it. It's not like there isn't a need for it. If you look at just organotransition metal catalyzed reactions, there are more than 60 billion pounds a year of product being made by organometallic catalysts, gaseous reagents under high pressure reacting with organic substrates. And so this was an important area for us that we thought was underserved by the existing instrumentation. And so what we decided to do, and what I'll talk about the remainder of my time, is develop a new high pressure NMR apparatus, which we call the Wisconsin High Pressure NMR Reactor, or WHIP NMR. And the goal of this was to solve the problem of how do you monitor reactions that take place in liquids but involve gases, and do it under conditions where gas-liquid mixing is not rate limited. And so our goals were to set up a device that was reasonably high throughput, could work with high pressures and temperatures, have excellent gas-liquid mixing, and allow us to simultaneously monitor the transformation as well as the speciation of the catalyst. So that's what I will be describing today. And so WHIP NMR consists of the several components. First of all, the high pressure is accommodated with a high pressure NMR tube, and we've fashioned special titanium based spinner housings that hold the titanium tubing and fit into a normal NMR probe. We need a gas circulation system so that we can bubble gas through the solution while we're measuring NMR spectra and while the reaction is occurring. So we built our own gas circulation system that can operate up to pressures of about 2000 PSI. In catalysis, what we'd like to do is to take our catalyst, often an air-sensitive catalyst, introduce it into the system, equilibrate the temperature and pressure, and then initiate the reaction, say, by injecting the substrate. So we need a high-pressure liquid injection system. So we've built that into the system. And then the final component is we like to leave this in the NMR magnet as long as we can. And so rather than take it out and wash it out each time, we built in a washing system that in about 10 to 15 minutes can wash out the entire apparatus and have it ready for another reaction. So that's the basic idea of WHIP NMR. I'll show you a picture and you'll see that all the hardware here hangs over the magnet. But here's a real example in real time of a rapid mixing experiment using NMR. There's a thin capillary tube that you can't see very well, through which gas is bubbling. And then we're injecting, in this case, it's an acid-base reaction. So we're injecting the acid in, it's neutralizing the base, and the indicator turns from blue to yellow. So there's about 2 to 3 second mixing time in this version of a rapid mixing apparatus. And so even if you're not interested in high pressure, you can do rapid mixing experiments using this with NMR. A lot of you may be wondering, well, if you have gas bubbling through the NMR tube, don't the line shapes suffer? And as you might suspect, yes, they do. They're awful. And so we've had to build into our bubbling system and the pulse program the capability of bubbling the gas through the solution for, say, 1 or 2 or 3 seconds, whatever your relaxation time is, and then about 40 milliseconds before the injection and before the accumulation of a pulse, we turn off the bubbler, then we pulse, we accumulate about a half second or so of an FID, and then we turn the bubbler back on. So that's the basic sequence. In principle, if you could make your bubbles fine enough and small enough, it wouldn't be necessary to turn off the gas circulation while accumulating data. But in practice, we've not been able to routinely achieve those kinds of very small micron-sized bubbles. Okay, so that's the apparatus. Here's a summary of some of the abilities. So we can run at pressures from 1 to 70 atmospheres, temperatures about -60 to 170. We've used this routinely at 150 degrees, for example. We maintain gas-liquid equilibrium throughout the reaction. We maintain constant pressure. We collect both proton, phosphorus, fluorine, NMR, whatever you want. And with rapid mixing, about 3 seconds, and reasonably fast turnaround, certainly less than half an hour between experiments. So you can see in the picture on the right, the apparatus hanging over a magnet. We just got a new instrument in, and so we'll be redoing a lot of this. Okay, so let's take one example and work through how you can use reaction monitoring to accumulate a lot of data very efficiently. And that's really been the focus of what we wanted to do. And so here's a hydroformylation reaction. So the hydroformylation is the reaction of hydrogen, CO, and an alkene to generate an aldehyde. We do so with regiospecific addition of the aldehyde functionality to this carbon. In the process, we generate an enantiocenter, and we do so with very high enantio selectivity. And so we were interested in questions like, during the hydroformylation, is the Z isomer of the substrate, which is shown here, converted, or the E1 converted into the Z, and vice versa? So is there any equilibration of the substrate due to action of the catalyst during the reaction? We wanted to know, are we actually maintaining hydrogen and CO concentrations in solution? And also we wanted to know what form is the catalyst in during the actual catalytic transformation. And so we've done this in the WIP NMR. And so here's an in situ hydroformylation where what we're monitoring is the catalyst. And so the catalyst in its initial form is this doublet, which is a rhodium hydride, as it turns out. But during the catalytic reaction, I'm sorry, I misspoke there. This is a rhodium acetylacetonate. Under the reaction conditions, though, it's transformed into the hydride, which is shown here. But you also see that during the reaction, there's some other species. They're very broad. And it turns out that these species are metal acyl complexes. So we can begin to monitor the speciation of the catalyst while this transformation is occurring. Okay. We can also monitor the transformation of the substrate into the product. And so in this set of stacked spectra, what you see are the substrate. So this is one of the vinylic proton resonances. It's the one right here. And it is going away. And you see that during the transformation, product is growing in. So here's one of the product peaks. And then over here is the aldehyde resonance. If you look very carefully, you can also see that during this transformation, there is a formation of, there is a concentration of hydrogen, which is maintained throughout the reaction. So we are really maintaining a steady state concentration of hydrogen by bubbling the gas through the tube as the reaction occurs. In this same experiment, in fact, the experiment, all the data that I'm showing you right now was done in one afternoon. We are also interested in knowing more about the rate law of the reaction. Is it first order in substrate? Is it first order in catalyst? As I mentioned before, are we maintaining a steady state hydrogen concentration? So by using NMR, we can monitor enough features, and in a single reaction, we can start out at high pressure, we can lower the pressure and monitor the reaction for a while, and then we can continue to monitor the reaction at even a lower pressure. And what we find is that the rate laws during these time frames of different pressure are absolutely consistent with a rate law which is first order in the substrate. So we know the reaction's first order in the substrate, and we get rate constants. But as we change the pressure from 500 to 150 psi, you notice that the rate constants that we observe for the disappearance of the substrate are changing. And that means that the pressure influences the rate of the reaction. You can take these data, which were accumulated, again, all in one afternoon, and you can start to ask, how does the rate depend on the pressure? And what you find from this kind of a plot is that the rate is inversely dependent on the pressure. Ultimately, we figured out that there's an inhibition by carbon monoxide in the reaction. We can also determine that the steady state concentration of hydrogen in solution obeys Henry's law. And so we know that we are always at equilibrium saturation conditions for dissolving hydrogen in the reaction solution. So I think with that, I will end my short presentation here, other than to give you a teaser. You can actually use this under routine conditions and find out a lot of interesting things about catalytic reaction mechanisms and bulk rate behavior by using NMR. And so with that, I'm not sure how we want to handle the questions now, if we want to do questions here or save them all for later. So I'll let Jason advise us.
So thank you very much, Clark. I think if you have any questions, please, for one, please post them in the chat. I'll be monitoring through that point and we can open them up for discussion. If everybody's okay with it, what I'd really like to do is actually pass the ball next to Aritra, and we can move through our speakers, and then we can sort of open the floor to a more open discussion. Thank you very much, Clark. Again, inspired. I love that setup. You know, this is one of those things in particular. Pulling data for multiple changes during a reaction is one of those things that you cannot do without having this kind of technology. All right. So for our second speaker,
all right,
we're going to pass the mic over to Aritra. He is our youngest participant and actually has joined Pfizer about a year ago. Is that correct?
that's right. Yeah.
And so he comes to us originally from his PhD at Michigan State. He joined Pfizer, and what he's been looking at now is using flow NMR capabilities coupled to things like high throughput to look at reaction mechanism and small molecule characterization, and really, really creative sort of applications in that space. So please, Aritra, take it away.
Thanks. First off, thank you everyone for having me here. So yeah, as Jason mentioned, I work at Pfizer in a group called Structural Elucidation Group on the small molecule analytical R&D side. And today I'm going to give you a brief high-level overview of the type of flow NMR we use, why we use flow NMR. I'll give you a visual of the setup we have currently, and if time permits, maybe a couple of examples. So before I go into flow NMR, where do we use NMR for Pfizer? Well, offline use-wise, and this is probably well known, right? NMR has been used for decades now as a workhorse for experiments like structural elucidation of molecules, impurity characterization, potency determination, and so on. But over the last decade or so, we have been more and more heavily invested towards online uses of NMR for things like process monitoring, in situ characterization, kinetic studies, and so on. Now, before I go any further, one question might be, why use NMR at all for monitoring reaction, right? There's a question that folks often get asked, at least folks who are not directly involved in the NMR realm, at least. And again, this is something many of us probably already know, and that is NMR can provide almost unparalleled resolution, right, in terms of a very spectroscopic technique, like compared to things like IR or Raman. You can get in situ, you can do in situ characterization. As you're monitoring the reaction, you can characterize various intermediates and so on. It's relatively straightforward in terms of quantification when you're using NMR. Provided you're running your experiments correctly, the response factor is always going to be close to 1, right? And the other point is, like, when we think of NMR, most often everyone's mind goes straight to proton NMR, right? But we can always use things like fluorine NMR, phosphorus NMR, and so on. So that opens up like, multi-dimensions that we can monitor simultaneously if we use NMR as a reaction monitoring tool. And of course, it's also non-destructive. And this is only speaking of in terms of offline NMR use, right? The old school classical NMR tube kinetics. Currently, we have, in terms of flow NMR, we have 2 different setups. The one is a continuous flow NMR setup, which is provided by Brooker, called the Inside MR. So in that setup, what we have is, we always have a small volume of the reaction that's continuously flown into the NMR and recycled back, and we are detecting it as it's flowing. So it's a continuous flow setup. And more recently, we have also obtained a stop flow NMR setup. I won't be talking much about the stop flow. It's something we have obtained more recently, but I'd be happy to answer questions about that in the Q&A session. So going a little bit into more detail into the schematics of the continuous flow NMR. By the way, can everyone see everything properly?
Yeah, looks fine on my screen.
Okay. Cool. So for the continuous setup, it's essentially, you have a pump close to the reactor that pulls in your reaction solution through a jacketed line into the NMR and returns it. Relatively straightforward, but the entire setup is temperature controlled. The lines, the reactor, as well as the NMR. So you have a good control over your reaction environment. So why use flow NMR over some of the static, traditional offline NMR techniques, right? And this goes back to, all the benefits of NMR that I mentioned right in the beginning. They still apply in flow NMR, but you also have some added practical benefits. The first being, this is effectively an in situ monitoring technique, right? You only have a tiny volume of your reaction component outside of your reaction vessel at any time. And more importantly, you can essentially monitor your reaction under the same condition as you'd be, as process chemists would traditionally run their reaction, right? So we are monitoring it under the benchtop condition, if you will. And this becomes quite important when you're talking about reactions, heterogeneous reaction mixtures, right? Where mixing becomes quite important. The mixing itself can impact the kinetics of your reaction. In fact, this is something that has been shown by some of our former colleagues, like Dave Foley, where we have shown that, depending on how you're running your reaction, whether you're running it on an NMR tube or in your reactor itself and flowing it back and forth from the NMR, the kinetics can look drastically different, right? So this is something we have to be very cognizant about when we are doing this reaction monitoring studies, because how you monitor the reaction, you can directly impact the kinetics of the reaction itself, right? So you might not be looking at a situation that's representative of the real reaction. Furthermore, having this flow setup really opens up to a much more diverse reaction scenario that we can monitor using NMR. So for instance, situations like highly exothermic reactions, right? You'd be much more cautious if you're trying to do that in an NMR tube. Whereas if majority of your reaction is sitting in a nice temperature controlled reactor, you'd be more comfortable doing highly exothermic reactions that release gas, require inert atmosphere, and more importantly, controlled dosage. Certain reactions require controlled dosage of reagents. That's something you can do in this type of flow NMR setup. It's not something you can do in a traditional NMR tube, at least in a straightforward way. And last but not the least, this is probably one of the most important reasons why we are so interested in this flow setup. It really works. It works really well with orthogonal analytical techniques, reaction monitoring techniques. So, if you want to couple this flow NMR setup with something like React IR, you can do that. You can easily stick in a React IR into the reactor and monitor both NMR. In fact, you can monitor proton NMR, fluorine NMR if situation permits, as well as get an IR. You can even stick in a pH meter or an easy sampler to collect LC. You can do all of these, multi-dimensional reaction monitoring techniques simultaneously in a single experiment. So a single experiment can give you a very large set of data. And furthermore, the other use this modularity of this setup has is the fact that instruments like IR, it can be a little bit challenging to be quantitative with those techniques, right? So coupling it with something like flow NMR, and NMR being much more readily quantifiable, you can quantify IR trends, you can quantify Raman trends, pH trends, and so on. So that also helps as well. So what does it add up to? It adds up to the fact that, using this type of flow NMR, we can get a large number of data very quickly. In fact, very recently, we ran a reaction where we were using 3 different instruments simultaneously for a single reaction. So we can pretty much obtain 1 week's worth of data, that takes 1 week to analyze in a single day. So that leads to better process optimization, and that can eventually save you cost and time. So what does our setup at Pfizer look like? It's pretty similar to the stock image I showed you before. Our reactors are sitting inside a hood here. We have a 400 megahertz Bruker NMR relatively close to it, and we flow from the reactor through a coaxial jacketed line into the NMR and back, the reaction mixture. And within the hood, we also have an Easy Max reactor, a React IR and a pH meter as well, pretty much at all times. And we can also bring in other instruments if we need to. So this is just a close-up picture of our day-to-day setup, if you will, where we can use React IR and so on, along with our flow NMR setup. Just a quick overview of some of the specifications here. The temperature range that's recommended by Bruker is -5 to +60 for this setup, but we tend to push it quite a bit, quite often. I have gone above and below those temperature ranges a few times. This is an image of the flow cell, the NMR tube of this flow setup, and you can see it looks very much like a traditional NMR tube. So it fits with any 5mm probe. And that's for the setup. Last but not the least, the challenges. Now, I've talked a little bit about some of the advantages that shows up with the flow NMR, but there's several challenges that are unique to the flow setup as well. Well, the first challenges I would say is, not unique to flow, but to NMR as an analytical technique itself, which is sensitivity, right? NMR is relatively less sensitive over techniques like, let's say, UV. So monitoring extremely dilute conditions can be quite challenging. Monitoring reactions in complex solvent mixtures. So one thing I did not mention is, like, for all of this flow setup, most of the flow reaction monitoring we do it in non-deuterated solvent, right? And that works out just fine. We have if the reaction is pretty concentrated, we just run it as it is. If not, we can do solvent suppression pretty efficiently nowadays with various pulse sequences like wet. But if you have really complex solvent mixtures, like, recently an example would be I have faced is isopropanol and acetonitrile mixture. So you have a large number of solvent signals spread all over your NMR spectra. So that can be difficult to suppress and can hide a lot of your peaks of interest as well. Also clogging. This is clogging, leaking, etc. These are problems, that definitely takes place in this kind of flow setup, especially if you have if you're monitoring a reaction where solid can crash out over time. That's something you have to be very careful about. Extremely viscous solutions probably won't work very well in a lot of situations. Air sensitive reactions can be quite challenging in this type of setup as well, at least the setup we have currently. And also the challenges associated with acquisition. When you're flowing materials through the NMR, you have to be quite careful in terms of setting your acquisition parameters, because if you're looking at a species with a very long T1, if you're flowing it quickly, it might not, the residence time, if the residence time of the sample is short, then it might not magnetize properly, and now you have modulation of your signal intensity, and that can lead to some challenges in being quantitative. So those are some challenges that show up on a day-to-day basis when using flow NMR. That's something you have to keep in mind. How am I doing on time? Can I breeze through a couple of examples?
I think take through one example would be totally fine, and then we'll come back to some more detail after that. Thank you.
That sounds great. Yeah. So one example is this is a bit of an older example. So at one point, a couple of years ago, we were looking at Grignard reactions. Now, those of you who have handled Grignard, this alkyl magnesium bromide reagents, it's fairly, reactive reagents, right? They're fairly sensitive towards water and moisture. So what we decided is to run these reactions in this flow chemistry setup, in this continuous stir tank reactors. Now, the challenge with that is you have to have a very good understanding of the kinetics of your reaction. Like, you have to have robust kinetic models to design this continuous stir tank reactors. And the first tool most process chemists would think of for looking at reactions like this and building kinetic model is something like an IR. The problem with IR is it's not inherently a very straightforward to be quantitative with those techniques, right? So typically you pair IR with something like LC to quantitate the IR trends. Now, LC is not something usable in Grignard because it's, you quench the reagent whenever you throw it inside an LC column. So this is where flow NMR was super helpful. We were able to use flow NMR and couple it with React IR to generate quantitative trends, and that was used essentially by some of our process chemists to develop this continuous stir tank reactors. So that's one example. There are a lot of other works too. I'll stop here for now, but I'd be happy to chat about more examples in the discussion panel.
Thank you very much.
Yeah.
Okay, thank you guys also for continuing to populate the questions in the chat. We'll come back to those ones as we move through. So next, I'd like to bring up Yining from Merck. So Yining finished her PhD at University of Barcelona and then postdoc at Scripps Research Institute with Donna Blackman. That's actually where I overlapped with her. Phenomenal researcher, and more importantly, the work that she's been doing at Merck is illuminating. Both this is also a joke. Some of the work that she's done in terms of in situ analysis with photo induced NMR has been absolutely fantastic and a real beacon for the field. So with that, I'd like to pass it over to Yining.
Hey, thank you, Jason, and the other organizers for the invitation. It's really my pleasure to be here with you all today. In the next 10 minutes or so, I would like to share a very quick overview of the in situ NMR as a multifunctional tool to shed light on reaction mechanisms of photochemical transformations. So in the last decade or so, photochemistry is rapidly advancing in the field of organic synthesis. However, its adoption in the pharmaceutical industry has been partially hindered due to mechanistic complexity and a lack of tools to investigate those mechanisms. In recent years, the utility of NMR spectroscopy for reaction monitoring and mechanism studies of chemical reactions have further increased with the introduction of the in situ NMR, which is a combination of in situ light illumination and NMR spectroscopy. So in terms of application-wise, it enables the structural identification and time course monitoring of reaction components under irradiation conditions. Professor Ruth Koswin from University of Regensburg in Germany, she published the pioneering work on the NMR. And within Merck, we started building our own customized setup. And in the past 3 years, we have heavily applied this new tool to study photochemical reactions and impact ongoing pipeline projects. Our NMR setup is very simple, consistent of let me just pull my pointer. Consistent of a power supply, LED source that is variable in a wide variety of wavelengths, and the fiber optic to guide the light inside of NMR tube. Please note that the tip of the fiber optic was sandblasted in order to emit homogeneous light. And then this fiber optic is placed inside of a coaxial insert, which serves two purposes. It centers the fiber optic into the NMR sample, and it also prevents its direct contact with the sample. On the right side of the slide, there's a schematic representation of the NMR sample that goes inside of an NMR spectrometer. When we started building this setup, we had to improvise the different parts. But recently, as the NMR grows popularity and gain more utility, vendors have capitalized on these findings, have now made both the fiber-coupled LED and the LED NMR setup, tube setup commercially available. Since this new LED NMR illumination device allows us to run photochemical reactions inside our NMR spectrometer with in situ light illumination, we have applied it to obtain very valuable kinetic data and structural information of reaction components under irradiation conditions to inform mechanistic insights into reaction mechanism of photochemical transformations. Besides, we have used this new tool to invent the NMR actinometry as a facile and a practical method for quantum ion measurements, which is a fundamental parameter in photochemistry because it measures the efficiency of how the absorption of photon transforms into the product form in the photochemical transformation. Today, I don't have time to talk about the details of method development, but I would like to highlight the mechanistic value that this measurement would bring in the case study I'm going to present you shortly. So it was to point out that the LED NMR illumination device, all the advantages associated with it are identical to those of the conventional NMR techniques that has been very well explained in Aritra's talk. But one cool feature unique to the LED NMR setup is that it allows us to examine the reaction behavior in alternating periods of light and darkness. Such information could be super valuable for gaining detailed mechanistic insights into reaction mechanisms. And with this short introduction, I'm going to give you next a quick example to show how we leverage the NMR to obtain detailed mechanistic understanding of a photochemical reaction and how that knowledge was translated for better process understanding. So the example I'm showing here is an iron catalyzed cycloisomerization of this alkenol 1 to form this 5-exocyclic compound 2. And it was to point out that the reaction product is not stable towards isolation because the newly formed terminal alkyne tends to migrate to an internal position in presence of any traces of acid to form the thermodynamically more stable product. However, this described an instability of the product was not an issue for the NMR quantification of this species over the course of the reaction. As Aritra mentioned on his talk, NMR is a non-destructive method and does not require standards of this non-isolable product to obtain response factors for its quantification. So these two qualifications combined made the NMR the perfect tool to monitor this unstable reaction species over the course of the reaction, as you can see on this stacked spectra of proton NMR. So another advantage of the NMR spectroscopy highlighted from these kinetic profiles is that it's a fast technique enough to capture induction periods. Capturing and understanding induction period could be bring us very important mechanistic insights into photochemical transformations. For example, in this particular case, the presence of an induction period tells us that our iron pre-catalyst needs time to lose one molecule of carbon monoxide to become active and to initiate the catalysis. We then next utilize our NMR actinometry method to measure the quantum yield for this transformation. Once again, it's the number of molecules of product formed per number of photons absorbed. So the quantum yield of this cycloisomerization was calculated to be 3. And then without going into details of mathematical explanation about how we obtain this number, I just want to highlight what this number actually means mechanistic for this reaction. So one of the proposals for this quantum yield equal 3 is that our pre-catalyst needs to absorb 1 photon to become active by losing 1 molecule of carbon monoxide. And then the active catalyst can undergo 3 turnovers in the catalytic cycle before it gets deactivated, presumably by regaining a molecule of CO and reverting back to the pre-catalyst. So if this hypothesis is true, it means that they should be operating dark catalytic pathway for this process. So to prove that, we run the light and dark experiment as I mentioned earlier. And we obtained this plot shown in the slide that highlights the behavior of the reaction in alternating periods of light and darkness. A lot of information we were able to extract a lot of information from this one single experiment. For example, it became clear to us that there's definitely existence of dark catalytic pathway as the reaction kept progressing during the dark region. And then the fact that we are seeing a decreasing reaction rate of a causal reaction during this dark region, and also the presence of a second induction period that is required to reactivate the pre-catalyst after dark region tell us that despite that the existence of dark catalytic pathway in this reaction, we will still need a constant supply of photons to ensure continuous regeneration of the active catalyst to perform the catalysis. So to further kind of looking into the reaction mechanism, we decided to kind of like study the dynamics of the carbon monoxide in the reaction. The carbon monoxide ligands can be found either free or ion bound. And in order to obtain the reaction kinetic profile of this species, and also to overcome the low natural abundance of the carbon-13 nuclei, we enriched our pre-catalyst with carbon-13 labeled carbon monoxide ligands. And the different chemical shift between both ion bound and the free CO, as well as the very short relaxation time of this species, allow us the accurate quantification of this species over course of the reaction. as you can appreciate from this plot. So the yellow profile shown here corresponds to the carbon monoxide bound to iron, and the green profile here corresponds to those of the free carbon monoxide present in solution. So consistent with our understanding of the behavior of the catalyst, as the pre-catalyst activates via loss of one molecule of carbon monoxide to become active, we can see a decrease of the iron-bound carbon monoxide, and while the concentration of the free CO increases during both the light, when the light is on. And during the dark region, what happens like our active catalyst regains back one molecule of CO2, reverting back to the inactive pre-catalyst, which means that we can observe an increase of the concentration of the iron-bound carbon monoxide and a decrease of the free molecules of CO in solution. So with this observation, it appears that keeping CO in solution could cause the catalyst deactivation, because it could basically reverting our active catalyst back to the pre-catalyst. So then we wondered if would be beneficial for the reaction by removing the CO from the solution via purging. However, to our surprise, by removing the carbon monoxide from the reaction actually proved to be detrimental, as it provided much lower reaction conversion compared to the control experiment. So what's the rationale behind that? Then we went back and reanalyzed the data from the carbon monoxide experiments, and we realized that when the occurrence of the carbon-13 carbon monoxide bound to iron could drop below the 2 occurrence, which is indicative that the existence of another catalytic deactivation pathway that will arise from additional carbon monoxide loss from the active catalyst to become inactive. Therefore, despite the apparent inhibitory effect of this carbon monoxide on the reaction rate, keeping the carbon monoxide in solution actually proved to be essential, because we want to stabilize the active catalyst as much as we can to minimize the possible deactivation pathway through additional loss of the molecule of carbon monoxide. Therefore, with all this understanding around the role of the carbon monoxide ligand in the catalyst, we realized and also proved that to obtain the best optimal reaction yield for this reaction, we need to use a closed system with minimal headspace. So I don't have too much time to talk about all the case studies, but I do want kind of to, before I finish, to draw your attention to this, the very, our latest work on the application of NMR to study the reaction mechanism of a photobromination en route to belzutifan, which has recently proved as a prescription medicine for the treatment of renal cell carcinoma. The mechanistic insights obtained contributed to define the commercial manufacturing process that is now being used for the validation and launch of the product work. So with that, I pass back to Jason.
So for our last speaker, definitely, James is another close colleague from the physical, organic, and mechanistic world as well. He obtained his PhD from Alan Spivey at Imperial College London. He then moved to Scripps Research, also with a postdoc with Donna Blackman, and then would join the pivotal and commercial synthesis team at Amgen Thousand Oaks. James now works on basically expanding the kinetic analysis platform. So this is really that space of cross and orthogonal techniques to really deeply look into a system. So James, floor is yours.
Yeah, thanks a lot for the kind introduction, and for the team at Ivan for the invitation to share some of the work that we've been doing at Amgen using our what we call our cryo-free NMR spectrometer. We're going to focus today on some reaction monitoring work that we've been doing that, and it's great to be part of this panel and see some of the excellent work that people are doing in other companies and in academia as well, using NMR for reaction monitoring. So At Amgen, we have this cryo-free NMR spectrometer, which was actually born out of a collaboration with HTS 101, who creates superconductors for various applications, including work with Boeing. And they collaborated with Bruker and Amgen, and this was really driven on the Amgen side by my very close collaborator, Maria. To develop this 400 megahertz instrument, and actually this is the only 400 megahertz instrument of this type in the world, and we're very fortunate to have it. You can see some pictures on the right hand side. This easily fits into a standard fume hood, and it doesn't require any cryogen refills or oxygen sensors, and we can very easily shut down the magnet during periods of non-use and start this instrument up again. We've actually fitted this instrument with a room temperature probe at the moment. This is obviously slightly less sensitive than the cryo probes, but it gives us the opportunity to run reactions at process concentrations. And we have a multi-nuclei probe in there, and we've got some demonstrated examples, some of which are included here, monitoring reactions with standard protons and fluorines, but also things like boron and silicon and lots of other things as well. And that really excites Marie in particular, when we could look at lots of different crazy nuclei in there. This is a really big advantage for us as we want to look into reaction kinetics. Being able to run at process concentrations is something that's really important, so that we can look at the kinetics under our sort of standard operating conditions. And so when we're doing this, we're currently primarily using the Insight NMR software from Bruker, which is used to program the spectral acquisition, as well as the standard top spin. And this is really dependent on the application. I think from our perspective, and I'm happy to talk about this with other panelists and people listening to the presentation, we found Insight NMR. It's certainly an emerging software. It definitely has some teething problems, let's say, but I think overall it's been pretty useful. However, when we're trying to do really fast sample acquisition down to sort of 1 second resolution for some of our faster reactions, then we typically try to use topspin and just use multi-ZG to actually program that through, and that would be just looking at one nuclei typically when we do that. I think that's one of the things we've found it's sort of challenging using Insight. And then when looking actually at the data analysis side of things, we use Mestranova for this. We use the reaction monitoring plugin, and again, I think this is emerging software as well. I think overall it does a really great job, but again, certainly we have had some challenges when using that, and I'm looking forward to some discussions today to go into that in a little bit more detail. So what we've actually done more recently, and this kind of goes with some of the setups that Aritra was showing, is incorporate this cryo-free instrument along with a lot of other process analytical techniques. Again, this fits very easily into the fume hood, and we've kind of built reactor setups around this so that we can very easily track the reaction using the cryo-free NMR spectrometer. We have a flow reaction set up with temperature control through an EasyMax and to control the tubing. So we have flow NMR there, and then we can incorporate other PAT such as React IR, React Raman. We use some calorimetry as well. And this allows us to not only monitor reactions, but also to look into things like reagent dosing, workups and crystallizations. And really this, is a game changer for us from a kinetic and mechanistic perspective. And NMR in particular has been really great for facilitating some of the kinetic modeling that we do, and for process optimization. So I'm going to just go through a couple of examples of some of the work that we've done with this setup, some of which is single tube analysis, and some of it's going to be with the flow setup that I showed on the previous slide. So the first example is from the synthesis of AMG 423, and it was to look into this radical benzylic bromination, which was the first GMP step in a 6-step sequence. This bromination was the first of a 3-step telescope process, and it involved the sequential semi-batch charging of N-bromosuccinimide, NBS, during the process. And during our scale-up, our late-stage scale-up, we observed some unexpectedly low yields and some new low-level impurities. And so we wanted to conduct a pretty detailed mechanistic study into what was going on here. And as is rather common in process chemistry, we'd been quite reliant on HPLC analysis during process development. And you can see some of that data shown on the lower right-hand side. The lines here are actually connecting data points. So there's pretty scarcity, of data. And notably using HPLC, we also couldn't monitor the concentration or quantity of NBS during reaction progress. So to tackle this, Maria and I teamed up to use our cryo-free NMR spectrometer. And as I mentioned, we ran this reaction in a single tube where we used very rapid heat up inside the preheated spectrometer to initiate the reaction. And for us, this actually gave us some initial challenges, getting the shimming correct and collecting the data of the quality that we wanted. This was actually one of the first applications of this instrument for process development. So, we were actually getting used to using it ourselves. And here we use the Insight software to automate multi-nuclear analysis. So in this case, we were switching between proton NMR, which would allow us to monitor the NBS consumption and succinimide formation, and then using fluorine NMR to monitor consumption of starting material and formation of the mono and the dibromide products. And actually, from this one rather simple experiment, we can gain, quite large amounts of data. Firstly, the rate of bromination is different to the rate of N-bromosuccinimide consumption, and this is really giving us a clue that NBS is not directly reacting with our substrate here to form these brominated products. We're then able to move through a series of kinetic experiments, which I'm not going to detail during the presentation, but I'm very happy to talk about in the panel discussion to kind of elucidate the reaction mechanism here. And actually through 5 rather simple batch experiments in the cryo-free NMR spectrometer, we were able to determine that the active reagent in this reaction is bromine, and this was causing us some issues as bromine was escaping the solution phase during the reaction, which was run above the boiling point of bromine, and so we had to consider reactor headspace. And we were able to create some models of both semi-batch and continuous addition modes to determine that if we moved to a continuous addition of NBS at a given addition rate, we could remove any concerns over bromine loss during this reaction. And you can see some of the kinetic modeling on the right-hand side of your screen. That was used to optimize this process, and this has been run on multi-100 kilo scale now and as a qualified process. And really this all came from NMR analysis in the cryo-free instrument, running a single tube in this case. So I'm having some problems changing the slide. I think hopefully you can see my nitration slide now. So yeah, the second example is this nitration reaction shown here, the nitration of an aryl boronic acid. We're very interested in converting this boronic acid to the corresponding nitro species. And after some initial screening conditions, we identified some conditions reported by Ola in 2004 for further investigation. And Ola had reported that this reaction proceeds via this very highly reactive TMS nitro species shown in the reaction scheme. However, one of the results that really intrigued us as we were looking into this was that the inclusion of water in this reaction seemed to improve the yield and also to decrease the side product formation, which was this chlorinated species during the reaction. And really, surely this highly reactive reagent wouldn't survive in the presence of water, and certainly we would expect it to inhibit this reaction. So again, we turn to the cryo-free instrument here to investigate investigate this further, we significantly decreased the concentration of the reaction to look at these kinetics, as the ammonium nitrate species is actually a solid in the NMR tube in this case. And again, we were in this using both fluorine and proton NMR. We also did some studies using silicon, which I haven't included on the slide here. And what we could see was that in the reaction in the absence of water, there was a pretty significant induction period at the start of the reaction prior to product formation. And that during this time, the TMS chloride was being slowly converted to the corresponding TMS alcohol as a result of water being liberated from condensation of the boronic acid starting material. And as this water was released after around 5 or 6 hours, the desired nitration reaction started to proceed. In contrast, when we included water in the reaction mixture from the start, we could see that the TMS chloride was consumed instantaneously to produce TMS alcohol, and that product formation initiated instantaneously. And this really kind of indicates that the proposed mechanism shown at the top of the screen, progressing through this TMS nitro species, was really unlikely to be the mechanism occurring in this process. Combined with some other studies, this actually allowed us to propose an alternative mechanism in which actually the TMS chloride was simply being used as a rather expensive method of producing HCl, and that hydrochloric acid was reacting with ammonium nitrate to release nitric acid. And actually the nitric acid was the active reagent in this process. So this led us to the next question: is can we simply use nitric acid to run this reaction and save sourcing some of these expensive and bespoke silo agents? And the answer was yes. We could actually run this using fuming nitric acid and obtain extremely high yields and very high purity material doing this. And again, we were actually monitoring this reaction using both calorimetry, which I've not included here, and some NMR, and some really quite interesting kinetics that we observed during this. And you can actually see that as this reaction proceeds, it actually gets faster and faster. And this is pretty unusual kinetics to observe in these sorts of, in any system actually. And that accompanied with the end of the reaction was this really large terminal exotherm. So I'm not going to go through the detailed kinetics on the figures at the bottom, other than to show you can clearly see, with very high data density, and you can see rate acceleration occurring as the reaction proceeds. And in the bottom right-hand figure, you can actually see that terminal exotherm. So this was only on 50-gram scale, and there was a really pretty large exotherm at the end of the reaction, particularly for the reaction shown in red. Again, combining this with some other studies, we were able to propose a mechanism that's actually in action here. So we believe that the nitric acid is slowly dissociating to produce this nitro radical, and that this is undergoing a radical substitution with the boronic acid substrate, and that any excess of your nitric acid towards the end of the reaction is actually starting to undergo autocatalytic dissociation, and that's producing a rather large exotherm and also releasing quite a lot of NOx gas as the reaction proceeds. And again, for those interested in some more details on this, some of our calorimetric studies, and I would particularly highlight safety considerations of this reaction as you scale it. We have a couple of publications shown here. So as I mentioned, we've also linked a lot of other PAT into these reactors now, and been doing some flow chemistry, some flow NMR, with this technique. Unfortunately, a lot of it is really something we're not able to disclose at the moment. So I've got one sort of simple example here, which again was related to some work on AMG 423. And this is some photographs of the setup as we were building it. So this was between myself, Andrew Cosby, and Maria. And what we were able to demo is that we could observe consumption of one of the starting materials, PIPA, using NMR flowing through the reactor setup. We could observe the other material, PCAR, using React-IR, and we can see the excellent overlay for both for product formation using both techniques. This is run at sort of elevated temperature. It's only 55 degrees, and we're using completely protonated solvent for this. And we've done a lot of other things since then using this setup, and hopefully this will become more freely available for us to discuss in the near future. Yeah, finally, I just want to acknowledge all the people on these slides, particularly Maria. There's a photo of her down here. We actually were really keen to see the setup that Yining discussed previously. We've actually adopted that and used it quite extensively for some photochemistry, shown here with Maria with her sunglasses on there for that. And yeah, I look forward to the discussion with the panel and everyone listening after the talk.
So yeah, and thank you guys. Really appreciate the lively discussion in the chat too. To kind of kick off, as I see the team that's sort of been assembled here, one of the biggest things as a comment about reaction NMR, because this is an interface between engineering, chemistry, physical chemistry, but there are many things that have to come together to make this work and sing. There's sort of two versions of this. So Yining, Clark, you guys have sort of adopted the kind of strategy of the reaction has to come to the NMR, right? So that's refitting the system so that the reaction environment is the NMR, the spectrometer itself. And then vice versa, the Aritra and James, these are more in the reactor is coupled to the NMR. So it's an ex situ kind of a point. Just quickly for both of you guys, pluses and minuses, what are the strengths and weaknesses of either of those two approaches from your things? And what do you guys, for somebody who's walking into this field, what would you advise them with in terms of considerations?
I guess I can start. Yeah, I think it depends on your problem. I'll say that for the NMR staff in my department, they become very nervous when we're carrying out the reactions in the NMR instrument. And maybe less nervous if it's being flowed through the NMR instrument. But I think there are certain kinds of experiments you can do in one setup that are very easy. When the NMR detector is the reactor, it means that there's faster response. There's you can easily do dosing. But yeah, I see options and lots of utility for both approaches.
And
oh, sorry, on you go, Yining.
Oh, thank you, James. Great talk, by the way. So I can add on that. I think sometimes, I think like Aritra showed, and also the work by Dave Foley, that they showed that how the reaction kinetic could be very different when you just have the reaction sitting inside an NMR sample, you compare to actually like kind of flow NMR setup. So I definitely agree with that, because the mixing everything is very different, right? When you're running the reaction inside an NMR tube, or when you're running a big scale in a batch setup, flowing the solution into the NMR spectrometer. But I do have to say that sometimes to get a quick understanding of the reaction mechanism, most of the time, like whatever the mechanism and the things you're going to get by running the reaction in the NMR tube will be applicable kind of like to the actual process. So it depends on what the goal there, right? If you really want to kind of like go through a development, like kind of optimize the reaction, okay, by changing this, how can we see? But most of the time, the data we get in solution, if it's a homogeneous reaction, it can be translated to the mechanism will not change, right, itself. The rate could, but I think the mechanism, if you have everything in kind of like in a sense set up, I think won't change. And then one of the caveat of the NMR, like when you're running in situ, is like there's no good way to run heterogeneous reaction, right? There's a lot of limitation like in that regard, or like involving gas. So that then in that case comes from the flow NMR, like they can do more creative solutions for that. So there's definitely limitation on when you're running the reaction inside an NMR sample, like static, or then that can be solved with flow NMR, which I feel like it's complementary. I think they're good because not everyone have this setup of the flow NMR. So I think, and also like, because it also has a lot of like engineering issues sometimes, because I know that you guys present a case study, but I'm sure that there's a lot of engineering manipulations behind that, like to make everything work as it is, right? But then, so I feel personally, I just found like when you just run a sample inside an NMR tube, that's the easiest thing to just get a very preliminary kinetic data to just kind of like justify whether NMR would be a nice tool to use for mechanistic understanding.
Yeah,
mean,
I completely, sorry, go ahead, James.
Yeah, I was just going to say, I mean, I think for us, and there's several people on the panel, particularly into reaction kinetics, right? It's all about getting the T0. And sometimes that can be pretty difficult to do in the single tube, right? And that's what we try to do as often as we can. And I totally echo what Yining has said. If we can run it in a single tube when it's homogeneous, that's what we're going to do. It's pretty easy to drop a tube into an NMR machine and let it rip. It becomes a little bit more of a challenge in certain cases where that's not possible. And again, Yining's absolutely right. We show the setup there and say it all looks pretty, but actually the engineering behind that, running reactions with the flow setup, particularly if you're trying to filter things as they're going into the NMR tube, leaks happen, things happen that, you see the end product, which is a pretty figure, but it's not always as pretty as that to get to that stage, I think is what I would say.
Yeah, I completely second Yining and James. Like almost, 90% of everything I try, I always try it in an NMR tube scale first, just to see like what can go wrong, right? Or if it is even worth running in a specialized flow NMR setup. And yeah, like exactly what James said, like getting the T0, it can become quite a bit easier if you're not running it in an NMR tube, because especially if you're running it in let's say low temperature, right? If you're trying to run something at like -20 and -30, you have to kind of inject your reagent that kicks off the reaction at a low temperature bath, drop it in the NMR. You don't know how much temperature fluctuation goes on in between all of that process. Getting an exact T0 could be quite difficult while you're doing all of that. That becomes a little bit easier in a controlled flow NMR environment. The thing you have to keep in mind is the residence time, the dead time, because now this depends on every flow NMR setup. It kind of varies, but depending on how length of your tubing and everything, right? When you start your reaction and when you can detect the first change, there is a dead time in that in flow NMR. So you have to keep that in mind as well. So.
Yeah, absolutely. While I have a ton of conversation I'd like to go on this, I'd like to make sure we engage our audience as well too. And again, thank you. So what I'm going to do is I'm actually going to call out to people that had specifically asked questions. If you can, please come off your mute, and I appreciate if you guys actually asked it. So Andrew Turner, you had a couple questions in particular. The original one was back to Clark about measuring O2 and other gas properties. Andrew.
Yeah, I mean, so I'm a process chemist by training and practice, and we love our palladium catalyzed reactions. And the big question is how sensitive are they to oxygen? So we either do it in a glove box and you've got no oxygen and it works, do it in a lab and chuck in a load of palladium just to cover urea basically. So I was kind of wondering, do you basically just sparge in ever increasing amounts of oxygen and kind of titrate in oxygen until you kill the reaction and find the sweet spot? Well, not the sweet spot, I suppose, but the dead spot. So yeah, really interesting. That was, I really like that. Thank you.
Andrew, I could say that we've never done the exact reaction that you're interested in. We've done lots of catalytic oxidations using O2 in the WIP NMR. But in principle, there's nothing that's difficult about doing that. And you could actually do it several different ways. I mean, you could not only use a mixed gas at a low ppm level and say at that ppm level, how long does it take to kill the catalyst? But you could also do things where you dose in an instantaneous concentration of O2 of a known amount and just watch the activity decay. So those are all pretty trivial experiments because you have good gas liquid mixing in the setup we use.
Cheers, thank you.
Yeah, excellent.
Yeah, I just say we haven't done that with NMR because we don't have that pretty awesome setup that Clark was talking about earlier, which would definitely like to have some fun with. But we've certainly done it in pressure EasyMax systems with React IR, where we just purchase nitrogen that has certain ppm levels of oxygen to allow us to set specs on that for scale up. So
Good to know. Cheers.
So in that same vein, Charles, and I apologize, your last name badly, Pathurana. You had a couple of questions specifically about setup, included things like solvent suppression. I know there was a little bit of discussion that sort of talked through that, but I would like to, because this is such an issue, right? We're talking about ideally measuring the reaction as it would run benchtop, and to go into specialized solvents and stuff is always a concern. So Charles, pass it over to you if you have any other comments, and I'd like to push that back to the panel in terms of tips, tricks, and advice in that sort of space too. So I saw you come off. Oh, there you go.
This is Charles. So yeah, we tried to use flow NMR quite a bit. So one of the main concerns from the chemist is that can we use protonated solvents rather than using deuterated solvents? So in the case we had to use solvent suppression, it doesn't work very well. So I'm wondering whether the panel has any input for me on this topic.
Yes, I can jump in on this if you'd like. We've tested a number of different solvent suppression methods, and a lot of them work. And it really depends a lot on the details of your system. I guess my recommendation would be, you have to test with quantitative samples that are set up so that they're standardized in a way that you can really determine whether or not, in the presence of solvent suppression, that the response still maintains the linearity with respect to concentration.
Yeah, really good advice. Guys, anybody else? Actually, on that, that's a specific, I think, a major thing people think about too. What does your pregame look like? So, you mentioned this, Charles, Clark, the standard bits of your quantitative calibrations for a system. Does anybody have any standard SOP of your walk up when you're kind of doing this beyond sort of drop it in and go? What do you guys typically adopt?
Again, I can say what we did is we first took a sample that had all the components that we're interested in testing and quantifying. And we just made several concentrations of those in the solvent that we were interested in, and tried, usually our setup was to try 4 or 5 different solvent suppression techniques. Sometimes sampling a variety of parameters for each one. It's a pretty fast setup though. I mean, it's easily automated. It's not too difficult to do.
Yeah, I would add to that. It's pretty much very similar for us as well, like standard samples measured in a couple of different pulse sequences, solvent suppression sequences. And one thing I do is also like try to measure the T1 to keep in mind, essentially like, make sure at least the nucleus of interest that you're trying to measure, right? Often it can skip our mind that, especially when you're flowing again, like that's T1 is something you have to keep in mind, because you cannot just increase the delay infinitely. It can be a little bit challenging to be quantitative when you're flowing your solution.
Yeah, and to add that, I think we definitely need to do like the initial screening about what the best nuclei to track the reaction, right? So whether it's phosphorus, whether it's proton, or whether it's fluorine. So that is kind of like initial, get the references and get everything, like basically to do the initial kind of study pre-work to see whether an MI is a suitable tool for that particular case.
I mean, yeah, generally we would try to avoid proton if we can track by other nuclei, because that gets rid of your solvent suppression problem straight away in most cases. And that's what we do. And yeah, I think the other thing is particularly to make sure that your NMR tubes are going to be stable when you put them in. You're not going to have any unwanted escaping of solvents inside your instrument is something else. So we typically use pressure tubes, even for room temperature reactions, just to make sure that there's nothing going to go wayward in there.
So again, further on this point, because a lot of the questions, and at least this, it seems like there's a general theme around the parameterization of what the hardware kind of looks like. In particular, Daniel, you were asking questions about line state limitations on flow and also uniform irradiation, specifically in the flows or the setup. So Daniel, could you join us and then we'll discuss through that point. While we potentially wait for them to come back. So Yining, specifically around that, when you have your centered thing, have you looked at, or do you have to consider irradiation through the sort of the axis of the tube? Is something that you have to calibrate against?
Yeah, so we do, like, the tip of the fiber optic was sandblasted in order to emit as much as homogeneous light as possible. So then we can, like, again, with our NMR actionary method, we can measure each time, calibrate, like if we want to measure the light intensity, because sometimes like over time, it might lose the efficiency. So we can definitely use our NMR actionary to, I guess, very simple like calibration kind of to see whether the light intensity still holds after a few usage. But usually like at the 410, like for example, the one that 445, the wavelength that we work the most, I think it's pretty stable. The light intensity does not decrease over time that easily. At 365, then you can burn the fiber optic sometimes, because when it's the plastic one. But then when you switch the glass one, then it's much better. So yeah, the tip is definitely some plastic in order to kind of try to emit as much as homogeneous light through the reaction sample. Otherwise, you would just have points that there's more light than the other, so you don't want that, right? So we kind of like our Mac Wisma from our bioengineering team in Canada, he kind of help us with that part, like try to sample the fiber optic tip so we can have as good homogeneous light as possible.
Yeah, absolutely. Clark.
Yeah, I was going to say that it seems like one way to solve some of the problems with non-homogeneity of irradiation would be to bubble gas through the solvent.
Yeah.
So that you make the solution heterogeneous, homogeneous.
So in that same vein, Kimberly, you're specifically asking about sort of volume limitations. So I think this is mostly in reference to something like the more sort of at or flow to, as opposed to sort of the point. Kimberly, if you're on, would you like to jump in?
Yeah, I do not work in the production area or a pilot plant. So typically the volume of our reactions are pretty small. And that has been a limitation, I think, with the flow NMR, especially if you don't bring your NMR right into next to the reactor, like your fume hood's at the other end of the lab, you got a lot of dead volume, as you mentioned, a lot of dead volume there. Therefore, you have to keep that in consideration of the volume of your reaction. And so I just was pointing that out, that's something people have to keep in consideration when going flow. That's all.
Yeah, actually, that's a very important point, because I kind of completely forgot to mention that when Jason, you asked the first question about how you choose whether you just run the reaction in the NMR tube itself or in the flow setup. Sometimes when we go earlier in the development, especially in our space, like sometimes we do not have that much material to go with the flow NMR. So yeah, definitely, that's definitely something to be considered. Choose which method we want to use.
Yeah, definitely. Like the lowest volume we can go in a more reliable way, at least, is about 20 mils or something. Going something smaller than that can get quite a bit difficult. Our line volume is about 4 mils total. So at any time, like essentially about 4 mils outside the reaction. Yeah, we have gone smaller, and we have another flow setup, not in our lab, but in a different lab at Pfizer, where essentially the setup is brought in much closer together, so they can go like 5 mils or something, something between 5 to 10 mils. But yeah, definitely volume is something you have to keep in mind.
But in terms of screening and stuff, if you, I believe, please, anybody correct me, I think there is such a setup as a microflow mixing and injection through rapid mixing, kind of like an adaptation to your setup, Clark, which would allow you to do effectively reaction slugs at a mil at a time, but multiple in series. So you're right, the burden volume may still be large, but you can imagine, chaining several of these together in terms of a screening event.
Yeah, I can speak on that. I think, Jason, you're talking about the Inside Express type setup like that Brooker has. It's,
potentially, yeah.
Yeah, it's a stop flow, fast injection flow NMR setup. So at any point, so essentially, I can actually share a slide on that. We just recently purchased it, so I don't have any chemistry on it. Oops. Here, this is what it looks like. It's this tiny flow NMR setup that's right next to our NMR. It essentially looks like this. It's just a fancy syringe pump essentially that's connected to a couple of different reagent bottles. Now, it doesn't have to be, right now we have really large reagent bottles attached to it. It doesn't have to be. You can have very tiny, about 1 mil of each reagents connected to each of these different syringe drives. And at any point, you can inject about 300 microliters of, let's say, syringe A, syringe B, syringe C, 3 different reagents into the NMR tube. Let that reaction take place. You monitor it, then you flush it out with a separate syringe drive, and then you inject it in a different ratio, let's say, to get different kinetic profile and screen through a variety of different reaction conditions. So that's something we're still playing around with. It's a very recent setup that we have. Does that answer your question, Jason?
Yeah, no, and again, these other kind of the intermix between the hardware adaptation and the application space is really, there's no end of what's amazing here. I think my first interaction with flow NMR, or not, well, just reaction NMR, was really taking a step back and doing that sort of like the Looney Tunes moment. Try it because you don't think you can't, and then it works, and then you're shocked, and then you sort of adapt from there. But on that sort of hardware integration piece, Shane Grosser asked a question I think was very relevant for implementation. So Shane, if you're available, could you pop on for conversation?
Yeah, sure. So yeah, the question I was asking, our experience in flow NMR at Merck in some cases has been kind of this ongoing concept of like, you need someone with like deep NMR expertise. You need a process chemist with deep understanding of the chemistry that's being done. You need a process engineer with expertise in the pumping or the valving that might be necessary, or the homogeneous reaction control for gas, liquid, solid systems. I'm part of my question is just like, what is others' experience in terms of like crafting teams with the requisite experience across the broad and diverse set of skills in order to make some of these, like you just said, Jason, like the intersection between hardware and application space be really productive. Curious to hear how folks have thought about kind of staffing projects like this.
I mean, I can tell you how we've kind of done it at Amgen over the last year or so is, really try and dedicate a couple of people to. We were focusing on using the instrumentation for reaction kinetics primarily. So I've been working very closely with Maria Silva-Lipe, who's an excellent NMR spectrometrist. And, she's been pretty brave letting me put reactions in there. And, she gets a little bit upset if the triplet doesn't have perfect symmetry. But, at the end of the day, that's not a massive problem when we're trying to collect large amounts of quality data. So she's been pretty brave going forward with it, and we've worked really closely. And she's actually in a different department to me, so we kind of got different management chains, but we've certainly had excellent support from our leadership to drive this forward as a sort of kinetics platform, and that extends out towards engineers that we work closely with in my department as well. So our chemists and engineers are both merged in our late stage process chemistry. So we work very closely with Andrew Cosby for any engineering issues around that too. And so between the three of us and then reaching out to other experts as we need to, we've been able to tackle, I would say, almost every problem we've been put in front of us so far.
So can I ask a follow-on question to your comment then?
Please.
So like, one of the things that our group is particularly interested in is this concept of democratization of technologies, right? So like from what you just described, it seems as if there's still a relatively small cohort that are kind of tasked with kind of deploying this specific technology to the broader parts of the portfolio, as an example. Is that something that you expect is like scale, like, can be kind of brought to the masses, or do you expect that this will continue to reside as a team, a diverse team, but a team that will have kind of dedicated subject matter expertise over the long run?
Yeah, so I mean, at the moment, that instrumentation is not open access, and I think that's probably been exacerbated slightly by the COVID. So basically, we can't have people working in the labs with us directly. We'd like the chemists to be as aware as possible of the instrumentation and our capabilities, and then come and work with us directly to implement that. We are a smaller department, of course, than some of the larger pharma companies, and so I think that rolls quite well at the moment for us, and we're certainly trying to expand the group, and hopefully we'll get some more manpower behind it given some of the results we've had.
Great, thanks.
So expanding on that part of it too, as we see, as you said, COVID and telepresence has been a major sort of impact to some of these things and scale up. But even in that point too, right? Does anybody have any comments about, as you said, the NMR technician being kind enough to let us near the system? This has been absolutely my experience as well. I've had phenomenal NMR support over the years. But what that does mean is, you walk up and you're like, hey, I'm going to be generating HCN in your NMR facility, and the answer is a hard pass, right? Like some of the time, this does become an issue, and just comments on that point. Where does that bridge go, and what do people see as paths forward for really expanding and opening these applications?
I think make the application much more user-friendly, right? Like, again, as mentioned earlier, when we talking about flow NMR, there's a lot of engineering. Like Shin also just mentioned, we have a team of engineering, like deal with the pumping and everything, like process chemists, but then if we make the instrument itself much more manageable, like in terms like you just put the solution in and then you press a button and then everything just starts working, I think that will definitely expand the utility. We use the FTIR, for example, right? That's just such a simple system that the adoption is being very, very widely because it's just very simple system to use in the lab.
Yeah, I second that. The interface of the flow NMR is getting simpler and simpler over the years, and it's getting to the point where you could potentially see, as long as you have a spare NMR where you can have a dedicated flow setup separately, like creating a type of open access flow setup. Now, having said that, I always see that you'll be needing a support team for that, for when things go wrong, right? Or training people, making sure, with all the technical challenges that come with flow, including leaks and other things. But you could potentially see, I could see at least having an open access flow NMR setup where, a dedicated region and NMR setup where, process chemists, if they need to study, they just go take their setup and run it the exact same way. And typically we use those EasyMax reactors, just run it in their open access EasyMax NMR flow setup. But again, I always see, at least for the near foreseeable future, needing a team at least to provide support in terms of things going wrong, or maybe an initial setup. But yeah, it is getting to the point where I think we could potentially have an open access flow NMR to democratize it a little bit better.
And that's why we introduced like yourself, Aritra, and some of the other speakers, the instrumentation of being able to have an easy max there with multiple other forms of PAT, because then people can really just come and replicate their process and run it through the NMR machine. I think the challenge is, particularly when you're not running, you know, in say deuterated solvents, or you're running at high temperature, then having an expert NMR spectrometrist there who's able to help with shimming, solvent suppression, all of those things that are maybe challenging to automate at the moment, is why we want to work so closely with them to make that happen, so that when we do it, we're collecting really high quality data that we can then use. You know, that's the difference between trying to do the sort of reaction monitoring side and simply taking a static NMR of a compound in your open access NMR instrument, you know.
Jason, if I can jump in for a second, that the comment I would make is, if you want to move this into everybody's lab where everybody can use it, we need to stop thinking about high field NMRs and looking at NMR spectra. We need software and small NMRs, benchtop NMRs, and think about the NMR the same way we think about an IR. Nobody interprets an IR spectrum. We look at changes in spectra, build a model, and monitor concentrations. We need to move that model if we're going to try and make this more democratic technique.
Yeah, well said. And to that, you know, this actually goes to the second point that I've seen in every one of your the demonstrations today in the panel. The NMR has the capability to produce these ridiculously just amazing insights, right? Small perturbations in reaction progress, like these small inflection points that, you know, to your point, James, you sort of mentioned it, onboarding all this other PAT is partially there to get the applications chemist to believe what the NMR saw. Right. And this goes back to Clark's point, NMR does not lie. Totally with you, but getting somebody to believe that that small inflection point is real. Comments, what do you guys feel, both as the practitioners, but also sort of, you know, the utilization of it? Where's the hurdle there of this small, you know, these changes? What do you guys see as the biggest leap?
Yeah, I think the challenge is to show that these small changes mean something to the experimentalist. You know, that it affects the yield, that affects the rate, that it's, you know, telling us something. And that's the whole challenge. It's not so much making them believe, it's making them believe that it matters.
That's a great answer, Clark. I'm going to add that to the banner I get that says NMR doesn't lie. You don't have to believe, you have to believe it matters as well. Okay, that's good. I like it.
We should be selling t-shirts, guys.
Yeah.
I will buy one. For sure.
Absolutely.
No, I think, and you just like these small changes that when we appreciate, like for example, even like pH changes, right? For example, right? It's NMR just such a nice tool, like capturing those like small changes in solution. When you see there's a pH change, you see your peak shifting. Yeah. And then that is actually, it's a very important information that we can obtain from the NMR spectroscopy. And then in one of the examples that I didn't have, the second example I didn't have time to talk about, that was like very huge observation we made when we saw a huge pH change. And then that kind of like induced a reaction to go to a cliff. And that's because there was huge like acidification in the reaction medium. So those things, I think it's just such a simple information you can obtain from one single experiment when you analyze your data. It's just, and it gives you so much information, so much insight into your process. It's just incredible.
Yeah, absolutely.
Yeah.
So a point that actually came up really recently in the chat too, and this goes actually, I caught it in Aritra, your conversation. You can run in a day an experiment that produces 3 weeks, 2 weeks to interpret the information. You know, the comment, Rikshiani, excuse me, could you please jump off into that point? What data is available to help you with this deluge, right? Like this becomes the bottleneck. It's not really the execution, but it's the interpretation.
Yeah. Sorry, was that the question or someone gonna jump in?
I'm not sure, are you still available, Rukshani?
Yep, I think
Okay,
she's online.
yeah, thanks for the opportunity. But yeah, I was wondering because some reactions we run like over like 12 hours or something, then we collect data with like 37-second data points over the whole period of time, and we are trying to process the data. So we get into trouble sometime with the software that we have. So we were wondering what sort of things in industrial wise or any other solutions that we can process the data quickly, fast enough to accumulate data, process them, get the either the orders with respect to catalyst or anything pretty fast way rather than doing them manually. Thank you.
Yeah, so that's a great question. So in terms of, I don't think I have a good solution in terms of combining data from multiple instruments of different type. For NMR, for instance, we just use MNOVA, and that allows us to gone are the days when you have to manually integrate every spectra and then calculate trends. So we can pretty easily get the kinetic trends from a bunch of different spectra in using MNOVA. But so going to Jason's point, we recently did an experiment. I cannot show the reaction, unfortunately. We combined IR. Let's see. Yeah. So we combined with IR. An easy sampler, which essentially fed into the LC, and NMR. And for NMR, we use proton and fluorine NMR. So essentially 4 sets of data, right? So we didn't have a good way to combine it. So essentially, I took care of the proton and the fluorine NMR part. We had a support for the IR as well, and she took care of the IR data, and there was an LC data as well, and we combined them. Once we put it in an Excel file, we then combined it to see how each of them correlates with each other, and gave us a lot of different, interesting, complementary insights. But yeah, I don't think there is at least we don't have a good solution to combine these different instruments into a single software package, at least for now. I don't know if anyone has any comments on that.
So I mean, we use a lot of Mettler hardware, right? And
Yeah.
I know that I've also been involved with Jason for some pretty cool online HPLC stuff, right? And anything coming through the Mettler software, you can push through iControl, which will then spit out spreadsheets that have all the data in there, and you can quantify everything from your React IR, your online HPLC, your pH meter, whatever you want, and that'll give you one spreadsheet that's already in pretty good condition. And then what we have to do there is manually add the NMR data to that most of the time. So that's where there's not quite the integration there yet for that, but everything else works pretty well through that. If you're using Mettler, I'm not so familiar with other pieces of hardware and software there.
Yeah, probably we should ask Mettler to incorporate NMR to their ecosystem.
Yeah.
Because I really like their ecosystem that have everything just talking to everything together.
Yeah, it's fantastic. It's fantastic. Yeah, and the addition of the HPLC to that recently has been a big advantage too. A little plug for Jason there and some of his great work on that.
Now, I have a comment that's not exactly answering Rukshani's question, but I think one of the more general issues that we have is when we have reaction progress or some sort of time course kinetic data coming from multiple sources, maybe not even the same conditions, the same reaction. How do we integrate all this together? And if I can, share one slide. Since we were told to be prepared to add things, and I'll just do this in a non-full screen mode. And I would say this is a general problem, is that we collect data from catalytic reactions. We may have non-catalytic data. For example, my group does a lot of work with looking at individual transformations that are part of a catalytic cycle. And the question is, how do we make sense of all these data? And I think what we need is we need better ways of coming up with what I'll call a comprehensive kinetic model, whether it's a microkinetic model based on every step in the reaction or not. And this is a real challenge right now. It's something that my group is working on, very intensely right now to try and figure out how we can do this in a robust way.
And I have to say, I'm so glad that none of you said Excel. But unfortunately, this is where the rubber hits the road still for a lot of the time, right? But you guys are right. Like this is a definite need in the areas just on the back end. Having high quality data is the first part, but the data to information transfer is still lacking. So a quick question for you guys on time. We're currently 5 off the hour. We're just a quick poll of the room. Where are we in terms of topic, and should we start, entertaining winding down? Because if you don't stop me, I will keep going.
Back in here. So yeah, well, we don't have to stop you if there's more to discuss. But if you would like to finish up right now, then we can do that.
First off, again, if anybody else in the audience has a specific burning question, you guys are in front of, 4 of the luminaries in the area. This is your chance to make sure you get the best information right from the source. So please, I encourage you guys.
Actually, I have a question. So I just asked for LED illuminated NMR, is it a like single wavelength setup, or we can use multiple wavelength to illuminate?
Oh yeah, you can actually use from, if I'm not wrong, like from 365 until 910. So there's multiple wavelength you can choose. So that's why I think it makes this tool very versatile, because you can run so many different wavelengths that you just have to buy the right LED source.
Okay, yeah, that's good. Thank you.
You're welcome. Thank you for asking.
A single wavelength at a given time, right? Not at the same time.
Yeah, like we have to change the LED. I think, but then the one that we have definitely have to change the LED. Like we have a 365 LED head, and then we have 445, and then we have also 515. Those are the major ones we actually use in terms of photochemistry. We don't want to go too low, because then the process itself is not safe if we want to below the 365. Yeah, but I don't know if Professor Ruth Coswin, they do have kind of like filter. You can probably also thinking about like having the big one and just filter out the wavelength that you don't, pick up the wavelength that you need. I'm not familiar with that. I don't know if Misha is online. I don't know if he, by the way, yeah, Misha is the one I worked on this work on the LED NMR, so he's definitely, I think he
I am online. Can you hear me?
Yes, we can hear you. You know if Professor Coswin has like a one and then they can just select the different wavelength, or has to use like single wavelength?
Single sources, yes. So it turns out that well, there are several disadvantages of using filters. First, filters are not really a point function, so you still have some sort of bandwidth, and you have the slope where at the edges of the filter, and also you lose a lot of intensity, and these sources are not very high power to begin with, so you end up with almost no light intensity at the end. And LED sources themselves, even though it sounds like a crazy idea, you need to buy each source for each wavelength, but they are excellent in terms of band selectivity. So it's almost a rectangle. So it gives you 445 plus minus 10 nanometers, and that's all you get. You don't get anything beyond that band.
And I think it's also pretty affordable, right, by each one, single ones. Thank you, Misha.
Sorry, any other comments, questions from the audience as well? If you have anything, you can either raise hand, or I invite you to just unmute, please.
I just say, yeah, the photochemistry setup that Yining and Michelle developed is awesome, and following their papers, we've been able to use it really successfully, changing different wavelengths and stuff. It's a really fantastic technique, and it works really well.
Thank you, James. Yeah, we love it. It's just the best tool.
Well, hearing no other questions, I wanted to just kick it one time open to our fellow panelists, and we'll go in reverse order. So James, Yining, Aritra, and Clark. Where is the dead volume, right? Not dead volume, but where's the blank space? What can we not see? You guys have presented ways of you push back illumination, but what, in your opinion, are we still really hurting for in order to look into these systems?
You mean what sorts of systems we struggle to monitor with the NMR at the moment, for example?
What would you, blue sky, what do you want? What's on your wish list to improve so you could see it there?
Yeah, I mean, I think, like, you know, being totally honest, I think heterogeneous, particularly thick slurries or crystallizations are still quite challenging, and I'm definitely going to follow up with some of the panelists after this to see how they tackle that sort of thing. I think that for us, that's probably the biggest challenge. And then, ironically, after Clark's excellent presentation, yeah, the gas liquid mixing reactions as well is something we would definitely like to be able to do more efficiently. So that's something I'm also going to follow up with as well. So that would be my answer.
Yeah, I agree, echo with whatever just Jim said. Yeah, because I think heterogeneous reactions that involve gas, I know that Clark has done a great job on that, but we have, I think it's something like we also need to develop here. Like even like biphasic, right? Sometimes reactions with biphasic reactions, how you to solve it, they're not very miscible. Like I definitely, there's some work done on that regard, but I think just having, because we have now this stirring inside the NMR, it really limits a lot of kind of reactions, right? So yeah, I think
that's actually the money shot, Yining. If we could develop a way of stirring reactions inside the NMR machine, then that would solve a lot of these problems.
Yeah.
Yeah.
I'll pull gas through it, man.
Yeah, yeah, no, it's solved. Yeah.
Yeah. Am I next? I'm trying to remember where we are.
Aritra.
Yeah. So yeah, along with heterogeneous, yeah, I definitely had quite a few struggles with reactions with things that are crashing out. Along with that, like viscous solvents, like sulfones, for instance, the pump struggles, like trying to pass it through those narrow tubes. I know, like, you know, one option is now switching towards thicker tubings, essentially with a larger density, but diameters. But then the problem becomes you have a large volume of solutions that's always sitting inside the tubing, right? So yeah, so it's always this fight between how narrow of a tubing you want to go versus, you know, what kind of solvent system you're trying to look at, you know, going to DMSO, then dimethyl sulfone, like, and then I've had some others that are like, it gets very difficult. The mixing within the NMR tube gets very difficult, and then that affects shimming and other things. So that, like, being able to handle that type of reaction more efficiently would definitely be advantageous. I would also say, like, fast reactions, right? With the continuous flow, looking at fast reaction is quite difficult because, you know, again, it depends from setup to setup. Our setup, it's about, with our current flow, it's about 2 minutes, you know, when you start in the reaction, when you start your reaction to the time it takes to get to the detector. But again, if you can shorten that time by reducing the length of your tubing, but not everyone has that option, especially because you have to run your reaction within a hood. A solution for that is those top flow setup, but that also has their own challenges because those things cannot handle heterogeneous at all. So yeah, there's always some caveats, right, in these different setups.
Yeah, I think everyone recognizes that heterogeneous reactions are a real problem for NMR. And that's just the nature of the beast. I think for us, the real limitation is taking a system like ours and making it so that it is more available, easier to set up. I mean, what we'd like to have is a little box that you just bring over next to the NMR when you need it, and you hook it up and you run for a day or two, and then you take it away. I think that the advent of benchtop NMRs is a huge change for making NMR more accessible, especially for our type of reactor, where we're interested in high pressure. People get nervous about high pressure that's not contained in a fume hood. And so I think that actually will have a huge change on us incorporating the style that we've taken into and making it more practical. Yeah, I would say, you know, what we would love, yeah, our particular setup is idiosyncratic. It's, you know, you guys were talking about what kind of teams of people do you need? Well, you know, we need an intrepid student and an intrepid NMR director. That's really all that's required. But, you know, we spend a lot of time doing fixing the apparatus, you know, developing new techniques. So our view is what we need is to partner with somebody who really knows how to do this in a commercially feasible way.
For sure. Well, thank you guys, and I really appreciate the conversation. And again, thank you to our hosts. It's been a real pleasure to have the opportunity to sort of to sit down with you guys. Unless there's anything else, I would like to call for last comments and thank everybody again for participating today.
Thank you for the invitation, and it's great to be part of this IVAN workshop today.
Yeah,
No,
Thanks a lot.
So we'll give thanks. Go ahead.
So-
yeah.
Sorry, Dave. Go ahead.
Oh, yeah. Okay. Yeah. So go ahead, John.
No, I'll add to all of this. You know, just absolutely fantastic talks and discussion today. We'll categorize this, of course, as practical applications of NMR, something near and dear to my heart. Good overlap into hardware methods, touched upon a couple of actual commercial pharma products as a result of all this. And as I say, I mean, you know, just very, very valuable material. You know, certainly our academic discussions are extremely important as well, but I always like to see the introduction of all this real world application stuff is very, very good to review. Thanks especially to all of our speakers, Clark, James, maybe you bring us a bottle of scotch next time. And Jason, Vinning, Aritra, very well done, very well done. A slightly different topic. I should have added at the beginning of the meeting, live Ivan live at ENC for 2022. Ivan will actually have an ENC suite this year for the very first time. That's in addition to our now traditional day before ENC meeting, but again, we'll have a Ivan suite running all week long. Little hangout place for you know, plenty of lively discussion, refreshments, and so on and so forth. But once again, anyways, thank you everyone for participating today. And Dave, back to you to close things out, if you would.
Okay, well, great. I have this nice gavel, Ivan gavel, that John got for me. So I now close out all the meetings with our Ivan gavel. So here goes. Thanks, everyone.
Thanks, folks.
Thank you, guys.
Thank you.
Thanks,
Thank you,
everyone.
everyone.
Thank you.
Everyone.
Bye.
Bye.